In this lecture, we will solve a series of phase diagram problems. Okay, so let's start with example problem number one. The problem states as following. Make phase analysis of the equilibrium solidification of lead tin alloys at the following points on the diagram, point D and point E. All right, so perhaps right away, I'm gonna copy paste the question, and that way we can solve point D in here and then point E on the next slide. All right, so first let me mark the point. Point D is right in here, okay? So I want you to envision the following, is that point D is a barely, a very tiny, infinitesimally small space above the 180 degrees C, meaning that I don't have to reinvent the numbers. I can just use the numbers that are already displayed on the screen. So basically what I mean by that, if I am to draw the tie line, right, it's not that blue line, but it's barely above it. But this would allow me to use these numbers, right? This and this. So if I am in point D, right, and I'm going to put it right here, point D. The phases that are present, we have alpha plus liquid, right? Because we are in that envelope with tiny space above. Now the composition of alpha is going to be 19.2 weight percent tin, right? Um, Meaning that the remaining 80.8 weight percent is going to be lead. For beta, oh, my apologies, I don't know why I said beta. For liquid, I'm going to have 61.9 weight percent tin, right? And then the remaining is going to be 38.1 weight percent lead. Right, so I just defined the phases present and I defined the composition of each. The last thing that I can do is that now I can identify the amount of each phase present, so or the weight fraction. For the alpha, keep in mind is that we're going to be applying the lever rule, right? So since I'm looking at the solid, I'm going to be using the numbers of the opposite end of the tie line, right? And that means, so I'm looking at the alpha is here, so I'm looking at the liquid. So it's going to be 61.9 minus 40 divided by 61.9 minus 19.2, right? I'm taking this space and I divide it by the entire length of the tie line. Now, if I am to compute this equation, it will give me 51.3 weight percent. Now, let's repeat the same for the liquid. Keep in mind is that for the liquid, now my liquid is to the right, so I'm going to be using the opposite end of my tie line, and that would give me 40 minus 19.2 divided by the entire length of the tie line, meaning I will have 69.9 61.9 minus 19.2, right? You will notice that the denominator remains the same, and then the answer would be 48.7. Now, before you move on, right, especially if you are completing a graded assignment, please make sure that the numbers add up to 100, right? Because if the numbers do not add up to 100, that's one of the ways to spot a mistake before submitting it to me, right? Okay, so now, oh, point D. Okay, I accidentally flipped them. I think I can flip them now, right? So this is point D, and now I'm going to complete the point E. At this time, if you feel very comfortable and you would rather work at your own pace, feel free to pause the video complete the question, and then compare the answers, your answers to mine. So for the point E, I'm going to be slightly below, okay? And if I am to do the tie line, it's going to extend all the way to here. Most common mistake that I see with students is that once they encounter that, let's say, point E, they don't really know where to stop. And how do I know where do I extend my tie line? Well, the tie line needs to intersect the line that separates the boundary. And this is why we extend it all the way through, because we are barely below the 183. And that means I'm going to be using these numbers, right? There's no need to come up with numbers that are very, very close but slightly off than what it is, because I want you to envision is that I'm drawing it and there is a space between the eutectic line and the line, the tie line that I draw for you, but this is mostly just for your comfort. But you have to keep in mind is that envision that that space is negligible, like almost invisible. And this is how I end up using the numbers that I see on a slide, right? So that means that for the point E, the phases that are present is going to be eutectic alpha and eutectic beta. The composition for the alpha is going to be 19.2 weight percent tin, right? And obviously the remaining is going to be the lead. And for the beta, it's going to be rich in tin, right? So it's 97.5 weight percent tin. Last thing that I would like to do is that I would like to calculate the percent fraction for each, right? For alpha and for beta. I will begin with alpha. So once again, I'm going to be applying the lever rule, right? So that means that at the bottom, for either, I will have the length of the entire tie line, right? And it's going to be 97.5 minus 19.2. And it's going to be the same in here, right? This doesn't change for either of the phases. But on the top, I need to make sure that I'm taking the opposite end. So since I'm doing the calculation for the eutectic alpha, right? And my alpha is on the left side of the screen. So I'm going to take the opposite end, and that would give me 97.5 minus the average composition of the alloy, which is 40, right? And if I am to compute this value, it will produce 45. No, it's not going to be um, point E, right? That doesn't look right. I will have to compute it with U, right? Um, mhm. So let me see. So that would give me 97.5 minus 40, and then I'm going to divide it by 97.5 minus 19.2, okay? So this gives me 73%, right? 73.4, right? Weight percent. So this is the fraction of alpha. Now, if I am to do the shortcut, right, so it looks like this answer shall give me 26.6, right, the fraction of the beta. But again, I would like to first compute it, right? Because I'm using a shortcut, but I want to make sure that I'm getting the right numbers. So now for the beta, I will be looking at the opposite end, right? And that would give me, so that is going to be 40 minus 19.2. Okay, so now let's plug in that into our calculator. 40 minus 19.2 divided by 97.5 minus 19.2. Okay, and the answer indeed is 26.6, meaning that this looks right. Okay, so this is weight percent. Okay. This is the fraction of each of the phases. So let me double check before I move on further. The reason I'm taking an extra time is because what I see on my screen before I actually made a mistake. So this is a point D, right? I'm looking at point D, so I'm above, and I'm looking at the tie line. Yep, this is correct. Now, now we are at point E, and that is going to be 97 minus 40, and then 40, yep. So everything looks good. All right, now moving on to the next problem. Um, so I guess the only challenge that I foresee in these problems, the concept is very, very simple. And usually, if you do end up struggling, that's either identifying where you are, and then the next most challenging point is that once you draw the line, sometimes students, they struggle to identify where to stop. Well, where to stop is you have to intersect the line, right? The line that separates the phases. And this is why in this particular example, right? I'm supposed to be like a lot closer, right? I'm a lot supposed to be up here and up here. I just kind of like drew it a little bit below. Okay, let's look at another question. So this time we're still working with a lead tin alloy. And it says that it contains 40 weight percent beta. Okay, so 40 weight percent of beta, and then the remaining is alpha. So just like that, I already know that I'm somewhere below 183 degrees, right? So I'm somewhere in this region, okay? 0.6 at 50 degrees. Okay, so I can draw this right away. I'm trying to do my best to draw a parallel line, but you have to excuse me. um, so if it doesn't look really parallel to the x-axis. Now the question is, what is the average composition of lead and tin in this alloy? This is a really cool question, right? So for the first time, we're flipping the question. Typically, we're given the average composition, we're given the temperature, we find the intersection, and from that point on, we start doing the entire phase analysis. Well, this time, we actually don't know that point, and we need to find that point, right? Well, like the point could be here. Actually, we don't really know where exactly that point, right? But I do have a suggestion for you. Just put the point somewhere on the diagram because it's going to help you quite a bit, right? So let's say if I am to put this like point X, I don't know where it is. It could be shifted a little bit left, shifted a little bit right, but I'm going to place it because it's going to help me visualize the things, right? Then I can put the tie line and I can start thinking, I can start compiling the equation. To proceed with this question, I can either use alpha or beta and the fractions that are given, but I will actually do both just to show you that regardless of which one you choose, the average composition is going to be the same. Let's start with beta first. Okay, so it says that I have zero point 0.4, that's the fraction for the beta. So how would I assemble this equation? I know that at the bottom I should have my entire tie line. So we shall start with the tie line, right? So in here, tie line extends all the way to 100%. And in here, the tie line actually stops at about, I'm going to assign it as 2%, right? I'm eyeballing it. You could have assigned it to 3 or 4, hopefully not 5, because 5 would be a bit too much, right? But I'm going to assign it to a value of 2, right? And then in here, it's going to be basically 100, right? So now from that moment on, I know that in here I'm gonna have 100 minus 2, right? And on the top, since I am looking, since I'm taking into consideration the composition, the fraction of the beta, I need to look at the opposite side, right? So my beta happens to be on the right, but I need to look on the left. And that means I will have some kind of value x. I don't know where it is, right? And maybe I placed it off, but it doesn't matter, but it's going to be x minus 2, right? So now if I am to solve this equation, and perhaps let's do it together, it's going to be 98 times 0.4 plus 2, and that would give me 41. So x should be at 41.2, okay? So technically, the average composition, and your x is going to be the 10, right? Because this is what I'm using. So it actually puts me at 41.2 right in here. This is where my real x is, right? But before I proceed with this answer, perhaps I can now erase it because as I said earlier, right, I'm gonna use the alpha to see, right, the other phase, which is going to be your eutectic alpha, just to see if I'm going to come up with exact same number. Because if I'm doing things properly, you have to end up in the same number because that x is the average composition of the alloy. It has to be the same regardless which route you proceed, right? Okay, so I'll switch the color and I'm gonna go now with the weight percent fraction of alpha, which is given as 0.6, right? Now, so I'm gonna just come up with the exact same equation, right? And it's gonna be 0.6 equal to, the tie line remains the same, right? So, and the tie line is gonna be 100 minus 2. This is our denominator. And the denominator, now I have to look at the opposite end from the alpha solid solution. So I basically need to look at the beta, and it looks like I have 100 minus x, right? So once again, keep in mind that this is your x, that in a sense, now we know what the number is, but we should assume that we don't know yet, right? That's the whole point of this exercise. Now I'm gonna have 98 times 0.6 minus 100, and that shall give me indeed the same number, right? 41.2. And as you can see, you end up with identical number regardless which way you proceed, right? So once again, you saw me early on. I didn't even think twice where exactly I should put my x. I know that my x is somewhere on that line, right? Because I know for me to be able to solve this problem, I need to have the average alloy composition. And then usually it is given, and that's how we find the intersection. So for simplicity, if you're solving a problem like that, it just helps you visualize where you should place it, right? But you should assume that this is now an unknown number, and this is how the rest is going to be just coming up with one of these equations, right? And regardless which way you proceed for this specific problem, either with eutectic alpha or eutectic beta, the alloy itself is the same, right? The average composition should remain the same. Now, let me challenge you a little bit. This is one of my favorite questions, and almost every year I do prefer to include this question in the examination. And typically, quite a few students are not able to solve it because they forget how to solve this specific problem. It's very similar to the previous one, but it has a little bit of a challenge in there, right? So I'm still looking at an alloy, but this time I am given the 60 weight percent of pro-eutectic beta, okay? So the key word here is pro-eutectic. We cannot ignore it. And if you guys remember, that's the pro-eutectic from here, right? That's the one that forms before. And then I have 40 weight percent of eutectic alpha plus beta, right? And I am like at a spot that is slightly below 183, right? But perhaps I'm gonna put this spot like somewhere in here, right? So I'm going to use this tie line, right? And you guys can see that I'm trying to draw it as close as possible because the delta t is extremely, extremely small. And for your convenience, you should actually place it very, very close so that the tie line would allow you to use these numbers. Okay, so that means that the next question is obviously calculate the average composition of the alloy. And here's the problem. When I'm looking at this 40 weight percent, right, and I'm referring to this 40 weight percent, that is alpha plus beta, right? In the previous problem, and I will scroll back in here, you could see that our information was given separately, right? We could have used either alpha or beta. But in this specific example, alpha and beta, the eutectic composition, we know it's 40%, right? So we're looking at something like this. So I know that this these pepperonis are actually, how much is it? 68%, right? The areas that I just shaded in red is 60%. The rest is 40%. But the problem is that the rest is combined as one, right? So I cannot solve it exact same problem. So how would I attempt this problem? Well, very simple, right? We're going to use the knowledge from the previous lecture that this proeutectic alloy that forms earlier, right, in this transition envelope is the same. And you can see it here. It looks the same whether here or there because the eutectic alpha and beta comes from the liquid. And so that means I can simply ignore the alpha and beta part. And what needs to happen is that I'm going to say that, okay, so my weight fraction is 0.6. But before I start drawing anything, I also need to go back into the right envelope, right? So that means all of a sudden I'm going to change the color. I have to be above the line, even though I'm given the temperature below, but because I'm going to be using the knowledge of um, the phase that forms before, earlier, it's a proeutectic. That means I have to actually find myself in the proeutectic phase, right? And this is why now I jump up. And again, for your simplicity, just put an X anywhere, like put it here, right? It doesn't matter whether it's a bit to the left or a bit to, you can actually make an educated guess and move it to the right direction. But that's given what your information that you're given. But that's not the point right now. For simplicity, choose the point, right? And this is going to help you visualize when you apply the lever rule, right? So that means that now the numbers I will be using is going to be this number and this number. So if I am to come up, and I'll keep the same color so you guys understand where things come from. So that 0.6 is going to be in the denominator is going to be the new tie line that is in the envelope that is above, right? It's not below 183. So hopefully you guys are on the same page with me why I went up there, right? So I went from here to up here because these pepperoni slices they have formed earlier, right? So I'm just going to go back where they formed and I'm going to use the knowledge from the proper envelope, okay? So, and that means that since I'm looking at the proeutectic beta, my beta is on the right side of the screen, right? So it's going to be here. So I'm going to use the distance to the liquid, and that is going to be x minus 61.9, okay? Now, from here, let's do the math. 97.5 minus 61.9 times 0.6 plus 61.9. And then, and I erased it. I erased accidentally. Okay. 97.5 minus 61.9 times 0.6 and then plus 61.9. And that would give me x, which is 83.26. And that is actually your answer. Now I'm going to the diagram and it is somewhere, if this is 85, we're roughly somewhere in here, right? And this is where you actually are, right? And this is how you approach a problem like that. Well, perhaps it is good to pay attention to the number that you got, right? Your number had to be above this 61.9, right? Because otherwise it wouldn't make sense, right? Because if you were anywhere below 61.9, you would be dealing with proeutectic alpha, right? So meaning that you made a mistake in math, right? So for us, it's just one of the ways to double check your own answer with this specific problem because you cannot do what you've done earlier, use alpha and then use beta and then compare the answer and make sure that you arrive to the same one, right? Because for this specific problem, the remaining 40% that they give you, it's when your alpha and beta is combined and we can't separate them and make the assumption, right? Um, However, now I'm thinking about the following is that now that you know the average composition, right, which is 83.26, I can estimate the weight fraction of alpha and beta. No, and it's gonna come up and back to 100%. Yeah. So the only way to proceed here is actually use the knowledge of the proeutectic alloy, right? And there are two main steps that you have to proceed. First, you need to recognize that okay, I can only use the knowledge of the proeutectic beta, right? Because that is the solid that formed before we crossed the eutectic temperature. But once you realize that, right, regardless of the problem, you could be on the other side. You could have a proeutectic alpha. But once you realize that it is so important to actually jump into the correct envelope, right? Because if you remain where you are, and by that I mean the original point, which is 183 minus delta t, then you won't be able to solve the problem correctly. Okay, well, let's look at a few more similar problems and see whether we can attempt those. I'm not going to go over all. I should have, I just realized that I never specified of what, of 10, right? 83.26 weight percent of 10. I should always do that, right? To make sure that the answer is complete. All right, so now we are given again a eutectic alloy, but this time it's going to be a copper silver phase. And again, they ask us to make phase analysis when you have 88% of silver and the remaining 12% of copper. And they give us a bunch of temperatures. Perhaps why don't we look at these two? Because I feel like if you can complete either of those, then the rest should be relatively easy. Okay, so I'm going to start with identifying the point on my diagram, right? So I'm looking at 88% silver. I'm making sure that my X is actually silver, right? And so that means that my 88% is somewhere in here. I'm going to go all the way up, and I will remind you is that for this specific problem, we're going to look at the point that is slightly below, and then we're going to look at the point that is slightly above, because this number right here, this line, right, it is highlighted as 780. So I'm going to be up here. Okay, so why don't I attempt the first problem where I have 780 degrees C plus delta T. That means first thing first is that I'm gonna draw a tie line, right? Barely above it. And then the numbers are actually already specified here, right? So this is your 91.2, this is your 71.9, and the average composition is 88. Well, this should be relatively straightforward. So I'm looking at the liquid plus beta, right? Now, the composition of liquid is going to be 71.9 weight percent of silver, right? Ag, right? And then your beta is going to be, it will have more of silver. It's going to have 91.2 weight percent of silver, right? Okay, the last thing that I would like to do is I'd like to estimate the amount of each phase, right? So I'm going to start with the weight fraction of the liquid. Again, one thing to keep in, so I'm in here, okay? So for the liquid, I'm going to be looking at the opposite side, and it's going to be 91.2 minus 88, right? That's the average composition. And then I'm going to have 91.2 minus 71.9. And if I am to complete the math, the answer is 16.6. That means that for the beta, I will have the following numbers. I'm now looking at the opposite side. I will have 88 minus 71.9. So I'm just looking at the numbers below there. This is how I come up with all of this. 91.2 minus 71.9. Denominator doesn't change. And the answer indeed is 83.4. And if I am to sum up both, it will give you 100%. And that's just one of the ways to make sure that we've done it right. Okay, now let's see what's going to happen if we go with the temperature that is barely below, right? So now it's going to be this purple point in here. So since I dropped below, that means now I'm going to have, first thing you do is that you draw a tie line, right? And this time the tie line is going to extend all the way till it intersects this curve right there, okay? So right away, as for the phases, and the point is going to be right here, okay? Right away, phases. So perhaps I'm going to first specify the temperature. At 78 degrees C minus delta T, I'm going to have alpha plus beta, right? These two. Now, the composition of alpha is going to be, I'm looking on the left side, right in here. It's going to be almost 8% of 10, right? And then for the beta, I'm looking on the other side, it's going to be very rich in 10, and it's going to be 91.2 weight percent of 10, okay? The last thing that we would like to do is that I would like to estimate the amount of each of the phases. So we're gonna go, oops, I accidentally pressed a button, so I'm gonna bring it right here. So this was my beta. Okay, so, or perhaps I shouldn't be in that spot. I'll put it right here. For the alpha, we're going to use the lever rule, right? The alpha is on the left-hand side of the screen, so I have to look at my right-hand side. So it's going to be 91.2 minus 88 divided by 91.2 minus 7.9. And this will give me the answer of 91.2 minus 88 divided by 91.2 minus 7.9. So the answer that I got here is going to be 3.84. 3.84, right? This is going to be the fraction. And right away, I'm going to apply the shortcut, and the shortcut shows me that I'm supposed to end up here with 96.2. Mm, did I get it right? Technically, yes. So, no, where do I get 0.4? My somehow. Oh, okay. I just realized that I'm keeping two significant digits, right? 96.16. Okay, so I decided to keep two significant digits for my uh, fraction. Um, solid phase alpha. Okay, so now let's double check. Let's see if we can come up with this number. I'm looking at the fraction of phase beta, so I'm going to be using the opposite end, right? And that will give me 88 minus 7.9, and the denominator remains the same, 91.2 minus 7.9. And I'm going to plug it into my calculator to see if I end up with the correct answer. 88 88 minus 7.9 divided by 91.2 minus 7.9. And the answer indeed is 19.16, right? So this is how we attempt problems with phase diagrams, right? Uh, to summarize everything we've done with the phase diagrams, um, it comes down to two key elements, tie line and the lever rule, right? If you, once you understand those two, you should be able to solve pretty much any problem, okay? And you probably noticed that a lot of problems are the same, and so they were designed to just swap the diagram and let you practice a bit more, and it all comes down to finding the correct position, right? And then drawing the correct tie line. During examination, the main challenge is that I will give you something that looks a bit chaotic, right? It will look a bit more, there will be a bit more phases, right? And I think this is something that you may encounter also in your homework. But again, it does not matter how many phases there, how many lines are there, as long as you know exactly where you are, right? First, you got to find that point, and then once you have your tie line, then the rest, the concept remains the same, okay? Now, a few more problems that I like very much. They're very, very simple, but I show you that we actually use eutectic point pretty often, and especially here, right, in our state, because it's very, very cold. And whenever it gets icy, we have city workers throwing salt everywhere on the roads, right? And we do know that the purpose of that is that it helps dissolve. Well, now you'll know how exactly it works. Whenever you are mixing ice crystals with the salt, you are actually trying to create a eutectic point. And you guys will see it here, is that typically, you know that at 1 atmosphere, right, at our standard atmospheric pressure, the ice melts only above 0 degrees C, right? But how do I melt my ice way below 0 degrees C? Well, let's look at this point right here. If you are to create a solid solution, and specifically you're going to have ice, which is kind of like gifted, granted, right, by winter, by Mother Nature, it's everywhere on our roads, right? And then all we got to do is that we got to drop approximately 23 weight percent of salt, right? Once we throw the salt, usually we throw a lot more, but guess what? That means that your composition is gonna melt, right? It's gonna liquefy, and it can do so at temperatures as low as -20, roughly 23 degrees C, right? So that basically is this is the beauty of eutectic alloys. And if you remember, that's what I told you when the temperature, the melting temperature of both, once you combine them, the melting temperature of the alloy is actually less than the melting temperature of each that comprise the alloy. And the beauty here is that if you actually deal with the composition of something that is a eutectic alloy, right, that allows you to go from a mixture of two solid crystals, right, ice and salt, you go directly into the liquid water, right? And that basically explains why the city workers they throw salt on the roads, right? Because they're trying to melt the ice by dropping the melting temperature. Okay, simply by changing the composition of the alloy. Okay, now based on the same diagram, suggest a process that would produce almost pure water from seawater. So hopefully we'll never have to do that, but it would be good to know, right? If we ever have to do pure water from the seawater. So seawater is about 3% salt. So we are somewhere here. This is going to be your 3 weight percent. So now let me go all the way to room temperature, okay? I'm gonna make all the way to here, right? So room temperature is roughly 20 degrees C. Now, at 20 degrees C, you guys will end up with salt water, right? It's a salty water. Now, how do I extract the pure water from the salty water, right? Just by using the knowledge of this phase diagram. Well, here's what we're gonna do. As you can see, we're gonna lower the temperature. And at some point, once we cross that line, right? And at some point, like once we go below 0 degrees C, what's gonna happen is that in that salt water, you'll be able to visualize the ice crystals, and this is pure water that is actually falling out of the salt water. And if I am to continue actually dropping the temperature down, right, you'll have more and more of this pure water crystals falling out, right? Let's call it ice. Anytime I say ice, I'm referring to the pure water, right? The solid water. And it's going to fall out of a solution more and more. And eventually, if you actually cross the eutectic temperature, I believe it is 23 degrees C, you'll end up in this position. If you continue freezing it right further and further, you will actually end up with two solids, right? And where you have a salt and you have the salt and then you have the ice, right? So if I am to make the water, what I would do, right, perhaps pause the video and think on your own how you would do. Question is very simple, right? Where do I stop? Like, where do I stop so I can actually enjoy a pure water? Well, somewhere here, right? Somewhere you don't want to cross the line all the way through, right? Because once you have two solids, it's going to be really hard to separate those two. They both are whitish, right? They both look like crystals. And then you would need to, of course, they will be different sizes and things like that. So the easiest way is to probably stop somewhere about that temperature where the majority of pure water is now actually is in crystals. And so what I'm going to do is that once I flip my glass, I'm going to drain the salty water out and then I can melt my ice and I can enjoy the pure water. Of course, there's going to be a lot of impurities, meaning salt actually still trapped in the solution, right, in real life. So you may have to do this process a couple times before you get to enjoy pure water. But it's just one of the ways how you can use the phase diagram to create pure water from the salt water, and how you can use the same diagram to melt the ice on the roads. Okay. Okay. Now, one more question. So we're looking at one more question. Explain what happens as 5 weight percent salt solution is cooled from room temperature to negative 30 degrees C. Give information regarding phases available. Well, I feel like I've already covered it, right? Because I've done an identical exercise. I've gone all the way through from room temperature all the way to below 23, right? And I've just done it to 3 weight percent. So perhaps we can just skip this question because I feel like I already addressed it. Um, Let's do one question with the sugary water, okay? So we have a sugar water phase diagram that is shown below. And question is, what weight percent sugar can you dissolve in water at room temperature? Okay, so how much sugar you can actually dissolve before you see crystals falling out, meaning that you've reached the saturation temperature. Since I'm going to assume that my room temperature is going to be 20 degrees C, and I'm going to go all the way up to here. And I'm gonna stop right before I reach this line, right? Right before. And it looks like, how much sugar is it gonna be? Well, if this is 70, perhaps it's gonna be roughly 65 weight percent, right? So theoretically, at room temperature, my number may be a bit different from yours because I'm doing it on the screen and it feels like my lines are a bit crooked, but roughly you can dissolve 65 weight percent of sugar at room temperature. Next question is, what percent sugar can you dissolve in water at 100 degrees C? So now I'm going to heat up my water, right? And I'm going to bring it to 100 degrees C. So if that is the case, I'm going to draw a line till it intercepts right there, right? And it looks like I can significantly increase the amount, and it's gonna come to roughly 78 weight percent, right? This is why sometimes, especially in some cultures, very sweet black tea is a part of the culture. And sometimes, if you let it cool down for a little bit, you can actually see sugary crystals falling out of the tea, right? Because as you drop the temperature, you're going from a liquid, right, pure liquid, which is sugary water, to where you have sugar water, right? And you also have sugar crystals in there. Okay, and then the last question for this module states the following. If 60 grams of water and 180 grams of sugar are mixed and stirred at the temperature of 80 degrees C, will this result in a single phase solution or a mixture? Well, that's a cool question, right? Okay, so I'm given the temperature. I'm going to be somewhere here. And again, I'm going to try to make a parallel line, right? So now, depending where I am, right? If I am to the left up to this point, right? If I am to the left from this point, then I'm gonna have liquid. But if I am to cross that line, then I'm gonna have liquid and some of the sugary crystals falling out of the solution. So I basically need to find out my composition, right? I need to find out where I am on the x-axis, and I'm gonna do the math for the sugar. Okay, so it's going to be 140 grams divided by the total, which is going to be 200, right? Which is 60 uh, plus 140. So the answer is going to be 14 divided by 20, right? And that is going to be, okay, I could have done it in my head, right? 0.7, right? Or 78% of sugar. So I am somewhere in here. This is going to be my 70, and I'm going to try to, okay, well, this is going to be challenging, and the answer will truly differ depending on how good you are with how stable your hand is. All right, assuming that that my line looks pretty parallel, right, to the y-axis. It looks like in part A, I will actually have a single phase, right? I'm going to have a single phase solution, which is going to be a liquid, right? It's going to be a sugary sweet water. Now, part B, what will happen if the solution mixture in part A is slowly cooled to room temperature? Well, what's going to happen if I am to take this exact same solution and to bring it to the room temperature? It's exactly what I've been telling you about the sweet tea, right? You'll see sugary crystals falling out of the solution, and you can actually visualize them, right? Because they look like a tiny crystals. Well, with this, we conclude our learning module number 5.